Now we're going to focus on the case of a series that converges under the integral test and see how we can use the same ideas that we've been using to prove the integral test in order to estimate the sum. So we're in the case, like in the integral test, where we look at a convergent series of non-negative terms because the terms of the series, the terms an, are really of the form f of n, where f is a non-negative function that is continuous and decreasing. And so the partial sums, sums of all the terms from 1 to n, form a non-decreasing sequence because we keep adding non-negative terms. And in the case where the series is convergent, let's call S the sum of that series, and we want to estimate it. Of course, the sum of the series, when is the limit of the sequence of partial sums, so it's the limit of a non-decreasing sequence that is convergent, and therefore it is really just the supremum of these partial sums. And therefore, one way to estimate S is to approximate it by a particular partial sum. So we add the first n terms together, and that's an estimate of adding all of the terms. And this estimate, estimating the sum S by a partial sum Sn, gets better and better as n increases. So as n increases, as we add more and more terms, we get closer and closer to the actual sum. At any rate, if we truncate the sum at a certain level Sn, then the error that we are making is really what we will call the nth remainder, and these are the sum of the remaining terms. In other words, the sum of the ai's starting at n plus 1. And what we want to do in the case when we are in the situation described for convergence in the integral test, in other words, where an is f of an, where f is a non-negative decreasing continuous function on the interval 1 infinity, and the integral from 1 to infinity of f of x is convergent, then we want to be able to control the size of the error we make when we take the nth partial sum to estimate the actual sum. So how do we proceed to do that? Well, let's draw again the type of pictures we've been drawing when we were discussing the integral test, and let's try to represent geometrically the error Rn. So this is the sum of the ai's, in other words, of f of I, where I starts at n plus 1 and keeps growing. So the first term in the series Rn is an plus 1, which we can represent by a rectangle with one side on the x-axis over the interval from n to n plus 1, and for the height, the value of the function f at n plus 1, in other words, at the right end of the interval. And we can do that for an plus 2, represented by a rectangle where one side is over the x-axis. It's a side of length 1, ranging from n plus 1 to n plus 2. For the height, we take the value of the function at n plus 2, and then we get f of n plus 2 for the area, in other words, an plus 2, and we keep doing that for all the values of the index, starting at n plus 1 and growing up to infinity. So that's a geometric representation of the error Rn. And you see that this area is less than the area under the graph of the function f over the interval started at n and continuing all the way to infinity, which is given by the integral from n to infinity of f of x dx, which is a convergent integral because we are in the setting where the integral from 1 to infinity of the function f is convergent. So that gives us an estimate of Rn from above. We can say that Rn is bounded above by the integral from n to infinity of f of x dx. But as we have seen when we were discussing the integral test, we could represent this same sum starting from an plus 1 plus an plus 2 plus an plus 3 and so on in a different way by just shifting our rectangles by 1 unit to the right, like this. Then all of our rectangles still have one side along the x-axis of length 1 and the other side corresponding to the value of the function at n plus 1, then at n plus 2, then at n plus 3. But now we have our estimate from below, because now the sum of the areas of the rectangle is greater than the area under the graph of the function over the interval starting at n plus 1 instead of n, and going all the way to infinity, which is given by the integral from n plus 1 to infinity of the function f, which is of course a convergent integral because of the assumptions we have made. And therefore, Rn is greater or equal to this integral from n plus 1 to infinity of f. So the error that we make when we estimate the total sum S by a partial sum Sn is between the integral from n plus 1 to infinity of f and the integral from n to infinity of f. So this is an estimate that will be very useful for us. And if you take this inequality and you add your partial sum Sn, what you use to estimate your sum, to each one of these terms, on one end you get Sn plus the integral from n plus 1 to infinity of the function. In the middle you get Sn plus Rn. But what is that? It's adding all the first n terms and then adding all the remaining terms. In other words, you get S in the middle, the exact sum. And on the rightmost term, you get Sn plus the integral from n to infinity of the function. In other words, we get that the sum is comprised between a partial sum Sn and the integral from n plus 1 to infinity of the function, and the same partial sum Sn and plus the integral from n to infinity of the function. So let's try to see how we apply this. Let's say we want to know if the series from 1 to infinity of 1 over n to the fifth is convergent, and if yes, we want to estimate the sum exact to 3 decimal places. So first, to know if it's convergent, this is easy because this is a p-series where p is equal to 5 and is therefore in particular greater than 1. So according to the p-series test, this is a convergent series. To estimate the sum, we can take a partial sum, but the problem is how many terms do we need to add up together to be sure that we will have 3 exact decimal places. So to have 3 exact decimal places, we want the error, which is given by Rn, by the nth remainder, to be less than 10 to the negative 4, because in that case it's not going to affect the third decimal. So how do we ensure that? Well, we have an upper bound for Rn. We know that Rn is bounded above by the integral from n to infinity of 1 over x to the fifth, which we can calculate as a function of n. Namely, an antiderivative of 1 over x to the fifth is negative 1 over 4x to the fourth, because it's x to the negative fifth, so you get x to the negative 4 over negative 4. And we evaluate this antiderivative between n and t, and take the limit as t goes to infinity. The value at t when t goes to infinity is going to go to 0, and what remains is 1 over 4n to the fourth. So that means that the nth remainder is bounded above by 1 over 4n to the fourth. And what we would like to do is make sure that n is large enough for this Rn to be bounded above by 10 to the negative 4. Well, we can do that by bounding 1 over 4n to the fourth by 10 to the negative fourth. And then we solve this condition for n. So if the reciprocal of 4n to the fourth is less than or equal to 10 to the negative 4, that's the same as saying that 4n to the fourth is greater or equal to 10 to the fourth. Then we divide both sides by 4, take the fourth root on both sides, and we get that n must be at least 10 over the fourth root of 4, which is approximately 7.1. Of course, n here should be a positive integer, and therefore the first value of n that is going to satisfy this condition is 8. So what that tells us is that the partial sum S8 approximates the actual sum S in a way that will have 3 exact decimal places. Now we can calculate this 8th partial sum by just adding together the first 8 terms in the series. Namely, we take 1 plus 1 over 2 to the 5th plus 1 over 3 to the 5th and so on, and we stop at 1 over 8 to the 5th. We can plug that in a calculator, we get an approximate value, and we know, because of the calculations that we have made, that the first 3 decimals are exact. Now, in fact, we know a little bit more, because we can use this improved estimate to get a lower bound and an upper bound for the actual sum. Namely, the actual sum is going to be between this 8th partial sum S8 that we have calculated and the integral from 9 to infinity of the function, which is 1 over 4 times 9 to the 4th. And then on the other side we have S8 plus the integral from 8 to infinity of the function, which is 1 over 4 times 8 to the 4th. We plug things in, and this is what we obtain for the approximate values. And you see that in fact we have 4 exact decimal places, because we have the same first 4 decimals on both sides, and therefore they are necessarily exact, because S is between these two numbers. However, you see that we don't have the 5th decimal place, which is not the same on both sides. So that should give you an idea of how to proceed to obtain estimates for the sum, where we're looking at a convergent series that is convergent thanks to the integral test. Now it is time for you to turn to homework on the integral test before we turn to comparison tests.